All right, torque, take two. Torque is represented with Greek letter tau, okay? And it can be thought of it as a rotational force. And this torque will have unit of meter newtons, okay? This is not same as joules. So to understand torque, you must start here at this pivot point. You have to know where this pivot point is in order to get this thing going. So draw where the pivot point is. Draw this first. Then everything else is measured from that point. Okay? So if you were to apply force onto this lever at this much distance away, right? That distance from the pivot point to where the force is applied is R. Okay? And this force right here, whether it's applied at an angle or not, doesn't matter. But it would definitely affect how this torque is going to be calculated. So if I were to apply this force at an angle like so, and I'm going to say that this force can be broken up into its components along this radial direction. So let's say that this distance from here to here is R. Okay. So this distance is R. The force acting at that location is F. This F, I'm going to be breaking this up into its components relative to the R vector. So this force and the R component of this force, like so, okay? So this force push perpendicular it's going to rotate this lever, and this force that is parallel to R, right, is going to do no rotation at all whatsoever. Okay, so this force push parallel to R does no torque. This force, however, right, this F push perpendicular to R, right, will give you the maximum torque. Okay? Because this force here will not really contribute to the rotation of this lever arm. Only this component of the force will. Okay? Another way of looking at this is if this is the line of the action, right? Let's say this is the line of the action where the force push is. Now, this is second way of looking at it, okay? The radial direction from the pivot point that is perpendicular to this line of force action, right? So I'm going to say line of action of F push. Right? The radial distance that is perpendicular to this line of action okay, this would be R perpendicular, right? R perpendicular, which is 90 degrees to the line of action, okay? Right? This multiplied by this force push will also give you torque. Okay, so there's two ways of looking at this. Either this R times this force perpendicular to R, or this force times R perpendicular to that line of force, the line of action. They're the same things. Okay. When we do some more example problems, I think it will make it more clear. However, that those two are two exact things that you can view it as. Okay, but you have to pick one or the other. You can't do both, right? I mean, you can do both, but you have to select one or the other method. Okay. So the lever arm distance, where the force is applied, right, is equal to torque. Now this is measured in meters, right? And of course, this is measured in newtons. And that's how we get meter newtons. Okay? So how does changing the direction of force push change this? Well, depending on how you push this thing and which angle you push it. So if you push it at a perpendicular to my lever arm, right, you get the maximum amount of torque. But if you push this parallel to my lever arm, you'll get no contribution to rotation whatsoever for this force. Okay? So when R perpendicular, when this right here is perpendicular to my force, right, you get the maximum amount of torque. However, if you get this force that is parallel with, notice how my R just shrinks to the line of action. My R perpendicular to the line of action is 0 in this case. So you get the maximum amount when this force is perpendicular to my R. Okay? So I guess you could say R perpendicular, right, is equal to maximum, right, when distance, right, from pivot point, right, to push, to F push, right, when F push is tangent. Okay? So you'll get the maximum torque this way. So F tangent to arc, right, will be maximum torque. However, if R perpendicular is equal to 0, right, if F push is radially inward, right, right, radially inward or outward, I guess, right, So if in that case, your torque will be zero all the time, right? So when F push, right, or the line of action, okay, okay, goes through the pivot point, okay, then torque is equal to zero. So when the and force is going this way towards the pivot point, it goes through it. R actually also, R perpendicular goes to zero, right? Because as this force, right, as this force goes this, notice the shrinkage of this, my R right here, right? It shrinks, shrinks, shrinks. And when it goes through the pivot point, my R goes to zero. My R perpendicular goes to zero. Okay? So when R perpendicular goes to zero, when this shrinks to zero, because this line of action approaches to the pivot point, I get zero torque. Okay? All right. So hopefully that concept will stick, and then we'll move on with some more concrete example with some mathematical operations. Okay? So mathematical definition of torque is a cross product of two vectors. Now, we talked about cross products earlier in chapter 3, right? We had a dot product to figure out work. Well, now you have to use cross product in order to figure out torque. Okay? So let's take a look at a simple setup here where this right here is the lever arm, or this is like the lever, and here's the pivot point. So the R vector, which is from the pivot point to where the force is being applied, is my R. Okay? Then the force itself is being applied at that location at a certain angle, like so. So when this happens, what you need to do is you need to redraw this pivot point somewhere away from this. So this is the pivot point. Right? It's a pivot point, PP. Right? Then draw this R vector from this pivot point. So here I'm going to say it's like 7.7 centimeters. Okay? 7.7 centimeters. And it's going in the negative x direction. So here's my R vector. So here is my R vector. Then you draw your force vector. So I'm going to just say 3.5, but the angle has to be the same, right? So you have to really make sure your angle is this. So I'm going to do my best. Now you don't always have to draw this every time you do this, but I'm just going to show you visually what it looks like. So here's your force vector. This angle here represents this angle right here. Okay, this theta and this theta are the same thetas. So theta. So, okay. So visualizing this is the most important thing when you do cross product. always redraw this R and F setup from a common pivot point so that you'll see this angle, okay? And by mathematical definition, your torque is equal to R cross F, which means we're going to have magnitude of R times the magnitude of this F times the sine of the angle between R and F, okay? It has to be the shorter angle, not this other coterminal angle, okay? The sine of theta. The theta should be less than 180, okay? And here's the important thing. N hat. What does that mean? That means this torque has to be normal hat, right? Which means it has to be perpendicular to both R and F. But the direction of this N hat has to be worked out with using right-hand rule. So to find the direction of my R cross F, or the torque, you place your fingers along the R where your wrist is going to be at the pivot point. So you could only do it either this way or this way, right? But you have to curl your R towards your F in a shorter angle theta. So your angle cannot be greater than 180. So you could curl it this way, and your thumb represents the direction of the torque. So it is R cross F. In this particular case, my N hat will be in positive Z direction. Okay, positive Z direction. Don't get this mixed up. The order of R and F is very important. It's not F times R or, F cross R. It is R cross F. So the first vector must be R. That's where your fingers go. And then you curl it towards your force. And your thumb represents the Z hat. Okay? So if you want to think about this as your hinge, where your pivot point can go instead of your wrist, you could do it that way as well. Some people like to do it this way. But if you curl your fingers towards your F, then your thumb represents the direction of torque. Okay? So that's very, 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 very important. Okay? So recognizing this angle and recognizing the direction of torque is very important. Rest is just pretty much you already know how to do R, right? That's, rx squared plus ry squared plus rz squared square rooted is the magnitude of R. And F, of course, fx squared plus fy squared plus fz squared square rooted is magnitude of F, right? Because these can be in three-dimensional space, right? So R can be like shooting out like this way, and then F can be like this way. So when you cross them, you should be able to get torque that is perpendicular to the plane of R and F. Okay? So always use this to calculate torque. So this is very, very, very important. Okay? Okay. Okay? All right. So make sure the sine okay? It's different than dot product, which is cosine, okay? So you can look at it this way in two ways, just like the way we did in the first page, right? It could be r times the sine of theta, right, times f, or f times sine of theta times r. Because just like, finding the what do you call that, line of action and the perpendicular radial distance, which is that. This is r perpendicular, basically, right? Or just find the perpendicular force that's perpendicular to my r, which is that, okay? So you could do it either way, and then you'd multiply by r, okay? So r perpendicular times f, or f tangential, which is basically perpendicular force, or perpendicular component of my r, times r. So they're both the same things, okay? So whichever you want is the one you want to do it. So in this case, you are actually finding to visualize it. So here's your R, right? And then here's your F, right? So you're doing this. This is the F tangential, right? This is the F tangential, and this is R. For this one, to visualize that, so here is your F, right? And here is your R, right? This would be the R perpendicular to the line of my, right? This is the R perpendicular to the line of my action. Okay, so this is the line of action, right? So this times that will give you torque. Okay, this will be like the right angle right here. The right angle. All right, hopefully that visualizes it. So either way, it's going to be this, the same thing. All right then. So I'm going to do something new, and then I'm going to see if I can give you guys a breakout room. So see if you guys can work this thing out on your own first, and then what we'll do is we'll come back and go over this together. So it seems like you could probably do this in, I'll give you about 15 minutes. All right, welcome back. So here, if we were to take a look at this, F1 is,
Again, or the first time.
I'm sorry?
You need to screen share. Your screen.
Oh, really? Okay. Let's do that again. Can you guys see?
Yeah.
All right, good. Thank you. All right, so here, my force 1 is 30 newtons, and it is in the left direction, which is negative x direction, I guess. All right. So again, you don't have to draw everything out in scale, but at least draw the angles in somewhat of a scale so you can see the. Okay, so here's my F1. So my F1 is 30 newtons in that direction. Now, common pivot point is right here. This is the PP, right? The pivot point. So I draw my F1 at the common pivot point and draw my R, which is 1 meter long, okay, in this direction. So again, here's my R. Again, you don't have to draw this thing out in scale. So my R1 is equal to 1 meter, like so. Now, the angle between my F and R, if you were to think about it, so here's my like F1, and if my F1 is slid here, this is the angle that I'm looking for, right? So you can actually think about this being 60, I'm not 50, I'm sorry, 50, and this being 90. So the angle between my F and R is 140 degrees, right? So this angle here is 140 degrees, okay? So you can calculate your torque 1 as R1 cross F1, which is R1 has a magnitude of 1 times F1 has magnitude of 30 times sine of 140 degrees n hat. But which way is the direction of my n hat? Well, R cross F. So you have to curl it this way. And only way to do that is if your fingers are orientated like that and curling it this way, and my thumb represents torque, which is negative z hat direction. Okay, so this is negative z hat direction. So if you work this thing out, right, you get 1 times 30 times sine of 140, you get 19.28 meter newtons negative z hat. Okay, or simply you can rewrite this if you want to as negative 19.28 meter newtons z hat. Okay. All right. And what about torque 2? Torque 2 is going to be, okay, F2, which is this. Here's my F2. And my F2 is 50 newtons. And my R2 is same as my R1, really, right? Because the same distance away from the pivot point. So we can say, okay, here's my R2. So my R2 is equal to 1 meter. Now the angle between F and R happens to be, again, this is the same common pivot point. Well, if I were to draw this out like this is my 40 degrees because opposite angles, right? Then 90 is here, so 90 plus 40 is 130, okay? So this angle here is 130 degrees, okay? So you can say my torque 2 is equal to R2 cross F2, right? And that is 1 times 50 times sine of 130 degrees n hat. Well, what's my n hat? Well, R cross F, my thumb is pointing up, so that's positive z hat. Okay, so that's positive z hat. So if I work this out, 50 times sine of 130, and I get 38.3, right, meter newtons. Right? So if you want, you could say torque 2 is equal to positive 38.3 meter newtons z hat. Okay, I guess this one could be boxed off as well. Similarly, if you were to do torque 3, so torque 3 is F3, and my F3 okay, my F3 is 25 newtons in the negative y direction. Okay, so here is my F3, which is 25 newtons, and my R3 is from here to all the way here, and that's 2 meters long, right? It's 2 meters long. So here is my R3, okay? And again, this is the pivot point. So what is the angle between, right, F3 and R3? So if I were to extend this, like so, right, this is 40, this is 90, and this has to be then supplementary angle, right, of this 40 plus 90. So this has to be 50, okay? So this angle here is 50 degrees, okay? So we can calculate, right, my F3, and well, torque 3 then is equal to, right, R3 cross F3, and that is, R3 is 2 meters, right? So 2 times 25 times sine of 50 degrees n hat. So what is my n hat? R cross F is going to be in, therefore negative z hat. Okay, so this is 50 times sine of 50, and I get something like 38.3, right, meter newtons. So my torque 3 is equal to negative 38.3 meter newtons z hat. Okay. And last but not least, here we have 15 newtons going in this direction. So here's my F4, right? So F4 is 15 newtons. And again, my R2 is going to be 2 meters from the common pivot point. Right? So my R4 is 2 meters. Right? Therefore, here's the common pivot point again. What is this angle here? Well, it looks like if I were to continue this, this should be 40, and 40 plus 30, which should be 70 degrees. All right. Therefore, torque 4 is equal to R4 cross F4. Therefore, R4, which is 2 meters, times F4, which is 15 meters, sine of 70 degrees n hat. 30 times sine of 70, you get 28.2, right, meter newtons, and R cross F. positive z hat. Okay, so you can say torque 4 is equal to positive 28.2 meter newtons z hat. There you go. So these are all these 4 different torques. And that's how you calculate these 4 different torques. Now, I can ask you, what's my net torque? Wow, wow. How can I calculate my net torque? Well, sum of all my torque is equal to torque net, right? That is simply equals to, right, torque 1 plus torque 2 plus torque 3 plus torque 4. So if you add these up, negative, positive, negative, positive, right? These two will pretty much cancel each other out. So it's this and that, right? So this will be negative 19.28 plus 38.3 minus 38.3 plus 28.2, right? Meter newtons z hat. So if I add all these up, what do I get? I get my net torque is equal to, right? I get positive 9.92 meter newtons z hat as my net torque. Okay? So that's good to know. Okay, that's good to know. And you should be able to do some homework problems. Okay? Yeah. I don't want to rush through this. Um, well, maybe we can do some. Actually, this is over at 9:10. All right, you should be able to do homework problems on page 11, 12. No, you're going to have to do this moment of inertia. Yeah, let's get this out of the way because I don't think we can actually do the other homework problems if you don't know this moment of inertia, John. All right, so here we go. Moment of inertia. Consider a wheel made of many particles, right? Many point particles, right? So this is solid, actually, a solid wheel, but the solid wheel is made up of many point particles, right? We will calculate the torque on them for each individual particles. So if we were to look at this one particle, now we blew this up into macroscopic scale. So here we will calculate how much torque is going to be done on this particle, right? And then we're going to apply that to all other particles throughout the whole thing. So here, if I were to apply force in this direction, I can actually break this force up into its radial component as well as tangential component. Okay? That means, right, F radial, this will not do any kind of contribution to rotation, right? So this will cause no torque, right? So this uh, does not, right, does not cause rotation. Okay, so therefore no torque. Okay, however, this F tangential will cause all of the rotation, right? Okay, so even though we have this force right here, okay, so if I were to redraw this by sliding this force to the common pivot point, so this is the actual pivot point right here, right? And redraw these two vectors from the common pivot point, right? This is a PP, right? My R vector will be going like so. There's my R vector. And here is my F. This is my F. Here's my F, right? Now F can be broken up into F radial and F tangential, right? So F tangential is what's really causing this to rotate. So F tangential. This is F radial, right? If you want to, you can write that in there, but that's not really going to do any. Right? So here is my F radial. So what is this angle right here between R and F? This angle theta is actually this angle theta. This angle theta and that angle theta are the same things. So this F tangential is the opposite of my force. So F tangential is equal to F sine of theta. Okay. So this F sine of theta right here, this is basically F tangential. Okay? So R times F tangential n hat. Okay? So what is F tangential? F tangential is MA tangential. Right? But this A tangential is alpha R. Right? So if we substitute this alpha R into my A tangential, I get my F tangential is equal to M alpha R. Okay? So if I plug this into my F tangential, then I get R times M alpha R. So R and R, if I can multiply them together, I get M R squared alpha is equal to my new definition of torque. Okay? So if I add up all these mr squares, so depending on where it is, if it's here, right, mr squared, and here mr, this would be different r obviously, but mr squared, if I summate all these mr squares, because alpha is going to remain constant, because when it's turning, they're all going to be having exact same alphas. So if I add up all these mr squared alpha n hat, I get my net torque. Okay? So this, if you think about how F equals ma starts, right? So if you think about like how F is equal to ma, this is the inertia, right? This is the inertia of an object. This is the acceleration, right? And this is force, right? Remember, this is like the rotational force, right? This is rotational acceleration. Right here. Then this mr squared acts as rotational inertia. Like rotational mass. Okay, even though the mass times r squared is happening under it. Right? So this is going to behave as rotational inertia. It's going to resist from its changing from its current state this object is in. Okay, if it's at rest, it's going to resist from rotating depending on how massive this thing is from the radial distance squared from the pivot point. All right. So this rotational inertia is also known as moment of inertia. This moment of inertia can be thought of it as rotational mass or rotational inertia. Okay? So since this is constant, we can now say torque can be represented as summation of all this, right? And if we take this to an infinitesimally small thing, right, this becomes the total moment of inertia, right? So this is the total, right, inertia times alpha. All right. So, and then n hat, I guess. Okay. So this mr squared, or the sum of all the mr squared, is represented as I. So the moment of inertia is represented with capital I, and then capital I, which is for the particle, is mr squared. So the sum of all torque now is equal to I alpha. This is Newton's second law of rotation. Remember how we set everything up into net force is equal to ma, and then found all the other forces. So once we found, right, the rotations of all these torques for all these different torques, and we found the net torque, well, this net torque is equal to I alpha. Okay, so this is only true, mr squared, this is only true for point particles. And that's the bell. So we'll stop there.